In part 3 of chapter 4, we're going to talk about flags and we're going to talk about the logical operators. If we recall, we've done flags in last year. It's a variable that we use to signal if a condition happens to be true. It can assist us in creating alternative actions. Oftentimes it's a bool, but it doesn't necessarily have to be. It could certainly be an integer value, and we use them so that, if I change that condition, so I might assign a variable a certain value, but if something happens, in an if structure, maybe I want to reset the flag to a new value. That way, if that happens, then I know that something special might have happened in my program, and we can use that to help either terminate or continue moving on in a different way. So flags are important. I would have also called them a sentinel value, where it allows us to flag for a certain condition to occur. So just keep him in mind. So the logical operators, we discussed those in the past, that idea of the and, or, and not. We looked at the truth tables last year with the idea that under an and scenario, only time that they would be true is if A and B were both true. We would end up with a true statement. If either one of them were false, then we were going to end up with a false statement. And so we knew that they would only occur once. With the or, the idea that if they're both true, of course we get a true. If one is true but one is false, it's still true. If one is false but one is true, it's still true, but only when they're both false is it false. So the symbols are a little different. The compiler will give you a little bit of, hey, that's old school, that's an old way of thinking. So we use the two ampersands together to show an and relationship. We use two vertical lines, which is a shift key action on your keyboard to show the or. And then here's the logical not. And we used him for the equal, the not equal to. It negated the idea of being equal. And so we can use that to test for the opposite. So sometimes it's better to test to see that it's not equal to something than it is to test for it being equal to something. And that might be a way to eliminate an entire data set. Well, if it's not equal to this, then I don't need to worry about maybe half of a data set, and then I can move on to another part. So we look at the logical operators to create compound statements of relational operations, relational expressions to test. So that might take away some of the need for the nested if statements that we looked at previously, but not always is this the best way to go, and the same with nested ifs. So here we have two tests. The idea if these were both true, and so looking, is 12 greater than 5? That's true. And is 5 greater than -4? That is true. So the expression will evaluate to be true. So if I were writing this as an actual logical statement, I could do this. You actually don't need the parentheses on the inside of an actual executing line unless I needed to show some compound relationships, because I put several of them in there. If we go back and think about the triangle program, that was one where we used parentheses to show precedence. Hey, I want you to test this logical statement before that one. So like, let's say I wanted to test these as a whole, but I also wanted another statement in there. Then I could do that. I could put another expression in here of some sort with the idea that it will evaluate this as a whole first, and then it will append this whole result to this single result over here. So they both would have to be true. The or statement would have to be true along with this single statement here for the whole thing to be true. So there are a lot of convoluted ways to create these. I caution you when you want to do multiple logical statements in a test expression, because it can get a little dicey. The compiler is going to read it left to right otherwise. The and does have higher precedence over the or. So you do need to be careful when constructing a statement of this type, you know. So here we can see the idea that they tested as long as they both are true. This is the same as the nested if that we looked at earlier, but they created a compound statement with the logical operator so that if it was they were employed and they were a recent graduate, then they qualified for the special interest rate. If one or the other were not true, it was going to fail this step because it's an and it would execute down here. So, you know, if this is under a true outcome, but this would be the false outcome. So here we see the idea of the or. As long as either one of these is true, okay, so it could be true or true false or false true, this would execute. Otherwise, this would execute only if they both were false. Now, there's this interesting little thing called short circuiting. If this is true, then it will not test the second condition. So it doesn't matter what the second condition is. So it will short circuit if the first test is true. It will not test the second expression, okay? If the first one is false, it has to test to see if the second one is true because it's an or. Now, let's go back to this and situation. The short circuit occurs when this is false. So the short circuit occurs if the first statement is false. And we talked about short circuiting last year a little bit, but you definitely need to understand this moving forward. So if they're not employed, it will short circuit and do the else automatically. It will not test the second half of the logical statement. And then since there are more positive outcomes with an or, it will short circuit when it's true, but it will have to test if it were false first. So here we see the idea of negating. So if this is a true statement, so if income is greater than or equal to the minimum income, or years is greater than the minimum years, so they flipped the testing. Rather than testing to see, you know, are they meeting the basic requirements, they've changed the test. So if this is not true, okay, so let's say this returns a true. So let's say this is true, it's going to negate it. So if it's true that it's not true, saying that it's false, it will give this message here. If this gives a false and it negates it, then it's a true and will execute here. So this negation sign here will undo whatever this result is. So it's testing the opposite condition. Okay, and we did that last year where we looked at it from two different perspectives, and that's what this is doing, is it's looking at it from the other perspective. So the logical operator, the not, has highest precedence, followed by the and then the or. And we talked about that in order of operation. Okay, if the value of an expression can be determined by evaluating just the sub-expression on the left side of the logical operator, then the sub-expression on the right side will not be evaluated. That was the idea of the short circuit. Okay, that if the first test is true for the or, it will not test the second side. If it's false for an and, it will not test the second side. It's just going to short circuit. It's about saving time. This is runtime, and so we have to worry about runtime. So the more I have to execute, the more runtime it takes. And in what we do, that doesn't matter. But if you think about it on a larger scale, where you're dealing with, you know, a large scale program event, it could make the difference in how long it takes to return a result. So validating user input, we did a little bit of that last year, you know, just looking for the reasonableness of a value. Is it within the range that we want? Is it the menu choice that I have to look on my list? Is there a division by zero error? So those are things that we'll also be looking at. So here, it gave us an else statement here at the end. In the event that it did not fall into any of the criteria of a grade A through F. So if it didn't fall into any of those, then there must have been something about the invalid entry. As we move into subsequent chapters, we'll learn how to, just go back for user input and not worry about that. I mean, we're testing for it, but we can ask the user to come back again. At this point, we won't have that idea of looping back. So we can compare characters and strings. So characters, remember, are integer values, so I can actually test them for order. So this is testing to see, is A less than B? So this would return a true statement. If I did, is B less than A? That would give me a false statement. I can actually test its ASCII value. So in this case, looking, for like user entry, something like that, did they enter something that was within the range? I can always look for that in terms of case. Here they're testing whether or not it was a digit or a letter versus a string. I can also compare, and I can do this in C++. We can't do this in Java. I can compare names using the primitive relational operators. Is Mary greater than Mark is true, and it's looking for the first occurrence where they are not the same. And so in this case, it's looking at the Y and the K. Y comes after lowercase k in the alphabet, so therefore Mary is greater than Mark. So I can use relational operators. I can test them for equality as well. I can test to see if two are equal to each other. I can't do this in Java. So, I caution you that this is true for some languages, but not for others. And again, it's learning the nuances of a specific language. So here they're testing to see, is part number equal to this, and it's looking for exact case. Okay, as well as letters. I can't, look at alternate cases unless I've made that very clear. Okay, so it's looking that they exactly are equivalent to each other in memory. Okay. So as far as what we discussed today was the idea of using the logical operators with the relational operators, and that I can compare strings and characters.